Welcome to this video on mathematical reasoning, part of our Year 12 Mathematics series. Today we will explore simple and compound statements, logical operations, and truth tables. Let's review the learning objectives for this video. In this video, we will distinguish between simple and compound statements, understand logical operations and symbols, construct truth tables, explore logical equivalence, and look at techniques for indirect proof. A simple statement is a declarative sentence that is either true or false, but not both. We use variables like Hep and Q to represent these statements. In logic, truth values are represented by T, or the digit 1 for true, and F, or the digit 0 for false. A fundamental rule of consistency is that a statement cannot be both true and false simultaneously. Compound statements are formed by combining two or more simple statements using logical connectives. These allow for the construction of complex logical structures. This table displays the common logical operations we use, including negation, conjunction, and others, along with their symbols and meanings. The negation operation reverses the truth value of a statement. As shown in this truth table, if P is true, its negation is false, and vice versa. A conjunction is true only if both statements, P and Q, are true. This truth table illustrates how the operation behaves across different states. Continuing our look at logical connectives, let's explore further operation. In mathematics, the disjunction, or OR, is inclusive. A disjunction is true if P is true, Q is true, or if both are true. Conditional statements are represented as P implies Q. Read as if P, then Q. A conditional is false only when the antecedent is true and the consequent is false. This implication table breaks down the truth values. Think of a conditional as a promise. If it rains, represented by P, I will bring an umbrella, represented by Q. Next, we will cover some advanced logical concepts. Conditional statements have variations. The converse involves swapping variables, the inverse involves negating variables, and the contrapositive involves both negating and swapping variables. When building truth tables, the number of rows depends on the number of variables. With n distinct statements, there are 2 raised to the power of n possible combinations of truth values. A biconditional statement, written as P if and only if Q, is true only when both P and Q share the same truth value. We can visualize logical structures in various ways, such as using Venn diagrams for conjunctions, mapping out logical deductions, or exploring abstract equivalence. Now that we have covered the basics, let's look at how we apply truth tables in practice. When constructing complex truth tables, it is helpful to break down the expression into smaller components and evaluate them step by step. There are 2 special types of statements to remember: a tautology, which is always true regardless of the variables, and a contradiction, which is always false. 2 statements are considered logically equivalent if they yield the same truth values in every row of their respective truth tables. Logical tools are essential for constructing formal proof. We can use indirect proofs, such as proof by contraposition, by showing an equivalent statement is true, or proof by contradiction, where we assume the statement is false to find a conflict. For instance, to prove that if a number squared is even, the number itself must be even, it is often simpler to prove its contrapositive. If the number is odd, its square is odd. To conclude this video, let's review some key exercises and summary points. Take a moment to practice classifying different statements and building truth tables based on the rules we have discussed. Use this checklist to ensure you have mastered simple and compound statements, logical symbols, truth table construction, tautologies, contradictions, and proof by equivalence. De Morgan's laws provide us with a systematic way to negate conjunctions and disjunctions. By building and comparing the truth tables, we can prove the validity of these laws because the resulting columns match exactly. This is the most important equivalence in logic. It proves that the conditional and its contrapositive are exactly the same statement. Never confuse this with the converse or the inverse. Next, let's examine the proof table that demonstrates these logical relationships. Logic has broad applications. In computing, logic gates in CPUs use these principles to process data. In law, they help structure arguments and identify fallacies. In pure mathematics, they are used to construct rigorous proofs for theorems. Here are some practice problems to test your knowledge. You can try constructing a truth table, finding the contrapositive of a given statement, or proving logical equivalences. Please complete the assigned homework exercises to solidify your understanding of these logical concepts. Thank you for watching this installment of the Year 12 Mathematics Logic series. If you have any questions, please reach out to the Mathematics department. This video features content from various sources, including DeepMind and other educational providers. Additional visual resources were sourced from Canva, Vecteezy, and other academic platforms.